Good morning, and thank you for coming to my talk. My name is Juliana Sebolt, and I work with the Levy Lab at the University of Pittsburgh. Today I'm going to talk about addition spectroscopy of graphene nanoribbons. Before we begin, I would like to thank our collaborators at the University of Wisconsin-Madison and the funding agencies that have made this work possible. One goal of Levy Laboratory is to measure the electrical properties of materials at ultra-low temperatures and occasionally high magnetic fields. As a lab interested in quantum computing, we are interested in investigating the quantum properties of molecular scale systems that may one day be used to build quantum computers. A quantum computer controls a large number of quantum mechanical objects called qubits. And as we are particularly interested in spin-based quantum information, we want to be able to control the spin orientation of each individual electron and also couple spins together. We propose graphene nanoribbons, or GNRs, as a strong contender for this application as a qubit. GNRs stand out due to their bottom-up atomic precision and great variety with which they can be synthesized. Our motivation is to develop a spin-based qubit that will be within a graphene nanoribbon. GNRs are tiny strips of graphene about 1 nanometer wide and 10 to 50 nanometers long. GNRs are important candidates because of their atomically precise chemistry, which can be controlled with the precision of every atom during chemical synthesis. GNRs often have energy band gaps, and their electronic structure depends sensitively on their width and edge geometry. We want to use transverse electric fields to induce band gaps in GNRs that are metallic. When the electric field switches signs, you get localized quantum dot-like states. And this is what we're most interested in developing. A senior lab member, Aaron Sheridan, has studied GNRs using optical techniques already, while here we want to focus on transport measurements. From the bottom-up approach for atomically precise GNRs, the Studinski group from the University of Nebraska-Lincoln works on graphene nanoribbon synthesis. In this paper, they design a nanoribbon in which the chevron GNR backbone is decorated with phenyl functionalities and demonstrate the on-surface synthesis of these GNRs on gold. Using scanning tunneling spectroscopy, they can determine the band gap. Also, we see from Tyler Cocker's group at Michigan State University the use of light wave-driven terahertz scanning tunneling microscopy and spectroscopy to investigate 7-atom-wide armchair GNRs on a gold surface at ultra-low tip heights. These experiments show highly localized wave functions inaccessible by conventional scanning tunneling microscopy. More GNR advancement comes from Cromie's group at the University of California, Berkeley, where they show a technique for inducing metallic properties in GNRs by inserting a symmetric superlattice of zero-energy modes into otherwise semiconducting GNRs. To verify the metallicity, they use scanning tunneling spectroscopy as well as first principle density functional theory and tight binding calculations. They also show that the metallic bandwidth in GNRs can be tuned over a wide range by controlling the overlap of zero-mode wave functions through intentional sublattice symmetry breaking. And with all of this exciting advancement, we want to continue it by trying to probe the electronic states of the GNR molecules, sensing when an electron hops on and off of the molecule. To probe the GNRs, we will use the lanthanum aluminate strontium titanate, or LAO-STO heterostructure. This complex heterostructure is filled with a lot of interesting physics, but here we work with LAO grown on top of STO exactly at the critical thickness. This way, one can reversibly tune the conductivity of the interface. In our group, we have developed a method to modulate this metal insulator transition at the nanoscale using conductive atomic force microscope lithography, or CAFM lithography. How this works is we start with LAO grown on STO at the critical thickness. Contacts are fabricated that have contact to the interface. We then bring a conductive AFM tip into contact with the surface of the LAO. When we apply a positive voltage to this tip, it effectively deposits protons on the surface of the LAO. These in turn attract electrons to the interface, locally modulating the metal insulator transition. Similarly, when we apply negative voltage, we effectively remove the protons we deposited, erasing the conducting nanostructure we created. Using this method, we're able to create nanostructures as small as 2 nanometers in size at room temperature. And that leads to the likeliness of an Etch-a-Sketch technology, but truly at the nanoscale, where we can create a diverse array of devices using this method. The focus here is on a nanoscale single electron transistor, or SET. There are a couple different methods for creating the SET device using the AFM lithography method. First is shown here, where a nanowire is created between a source and drain electrode and also connected to voltage sensing leads. At the center of the device is a conducting island, in this image a quantum dot. The dot is created by pulsing a negative erase pulse at the intersection, followed by a brief positive writing pulse. The Coulomb peaks are shown on the graph of differential conductance from source to drain versus voltage of source to drain, showing electrons hopping on and off the island. In this paper, we see a quantum dash created between a source and drain nanowires using negative voltage erase cuts. There is also an electrical side gate which tunes the chemical potential of both the upper wire and the quantum dash. It modulates the tunnel coupling between the quantum dash and the external leads. At the center, the quantum dash is isolated by insulating barriers. Differential conductance versus side gate voltage measurements for the quantum dash exhibit a sequence of diamond-shaped insulating regions for specific side gate voltage values. Coulomb diamonds help identify the addition energies. The nodes are regions where you have resonance transition, and the diamonds open to the blockade region. Here we see more as to the importance of the SET, because we can control and see how many electrons are tunneling across the insulating barrier to inhabit the quantum island. We can see how sweeping the side gate allows us to tune the chemical potential and to allow electrons to tunnel onto the island when the chemical potential of the source matches that of the island. When the chemical potential of the source leads are between an occupied and unoccupied state, you get Coulomb blockade. An electron cannot fill the next state due to the chemical potential not being large enough to match that of the island. When the chemical potential of the source is raised to the next state, electrons are able to hop onto the island. Understanding the energies at which electrons choose to occupy the molecule give the addition energy spectrum, and this can help provide important information about the energy levels in the molecule. The ability to change the electron occupancy is also closely related to functions that are required for using the electron spin in a quantum computer. Now we want to look at placing a molecule or a GNR into our system coupled through the LAO to the quantum island. This will allow us to study the electronic structure of the molecule. And to get graphene nanoribbon powder onto one of our devices, we want to use a technique inspired by work done for optics by Erin Sheridan. In her experiment, she deposited the GNRs by putting a macroscopic piece of the GNR powder into an inkwell sample, and this can be something like a spare LAO STO sample. Then one brings an AFM tip into contact with this inkwell and scans in contact mode to pick up some of the nanoribbons. Then the tip is brought over to the desired substrate, and using contact mode again, GNRs are shed off on the LAO surface. Then one can identify where one of these nanoribbons or nanoribbon clusters is with an AC mode AFM scan, and then the device can be designed around. Another lab member who's giving a talk later, Ahmed Omran, is working to create nanovias or tiny holes in the LAO, exposing a region of STO. This allows us to place materials such as GNRs into the hole using a method similar to that just explained. GNRs are difficult to contact electrically because they are so small. We want to place GNRs into these nanovias that have contact to the interface. The initial experiments we are planning have the SET geometry, but the difference is the SET island will now be co-located with a single GNR molecule that can hold a small number of electrons. If an electron hops onto or off of the molecule, it will be sensed by the SET. And understanding the energies at which electrons choose to occupy the molecule will give us the addition energy spectrum. We can look for changes in the charge states of the GNR, again by placing it at the interface inside one of these nanovias. We want to create an SET device around the GNR with the GNR as the island to achieve better electrical contact. Here we propose to develop a new spin-based qubit based on the unique atomically precise properties of graphene nanoribbons combined with the nanoscale reconfigurability of the LAO-STO system. Using the SET geometry, we can study the addition energy spectrum and try to probe the electronic properties of GNRs. And with that, I would like to thank you for your time, and please go check out some of the other talks from our group.